Hello, hello, hello. Welcome back. It is, what is it? It is Wednesday, the 21st of January. And today we are planning on going through connected particles, slowly building up, but really leading up to the main event, which is going to be the lift problems. So if you're watching this sort of after the fact, you're not watching it live, there should be timestamps down below. So if you want to skip ahead to the parts that you need, feel free to do that. But in the meantime, I'm going to build it up a bit more slowly because I remember the exact session in which I helped someone with this topic. And I'm kind of with these seminar series going through the different topics that people have found particular difficulty with sort of throughout my career and how I explain those. And I find that lift problems, especially dealing with the reaction forces and which forces act on different objects, it's one of those topics that people really, really hate. So I thought it would be worth popping on nice and early in the summer cycle and making sure that people know what they're doing with those moving forward. Now, as always, if anyone drops in live, feel free to drop something in the chat. I'll answer any questions as we go. Also, while we're here, sort of a quick sort of parish announcements. I know I've had a lot of requests for a Discord server, something where you can see when I'm going live, and also have a bit of interaction. It's something I'm looking at. I know I've got to sort of up the sort of YouTube engagement game, and so I've got some time this weekend, well, mainly Friday. So I'll kind of look into it and kind of see what I can do to make it a better experience for people who are here looking to stick around as we move through to the summer. Now, I think a very good place to start would be, yeah, I've got a bunch of questions. As always, I'm not going to share any sort of paywalled content. I'm going to use the structure of the questions, though, maybe change a few of the values so that we can still use the questions as a scaffolding for me to then explain the concepts that I'm using. All right, so without further ado, let's move you over here, and then I can start sharing screen. Well, I can start sharing screen once I've deleted the paper I did yesterday from my whiteboard. And turn on my thing. We love preparation here. We are professionals. All right, so getting this shared now. Making sure you can see it. Okay, got my pen, all good. Right, so first thing I want to go through is making sure you're okay with the fundamentals of connected particles. This is always best done with an example. So let's say we had a car. Classic case would be a sort of car pulling a trailer through a tow bar, right? So let's say this was 1,200 kilograms, and let's say this was 400 kilograms. This is going to be the car, which is pulling a trailer. Now, an important thing to know about, well, the first thing with any sort of mechanics problem is to make sure you're drawing a really good diagram that includes every object and all of the forces acting on all of the objects. So here we know we have a driving force coming from the car. We also know that there's going to be tension in this tow bar. Now, tension, whenever you see that in a problem, the way to understand which way it's going to act is that tension pulls out. No, tension pulls into the middle. So tension is about pulling things together. So tension pulls into the middle, and so it's going to pull the trailer to the right, and this is going to pull the car to the left. It sort of resists the car's motion. We might also have friction or other resistive forces outlined in the question, as we do here. So let's say this one has a resistance of 100 newtons, and this one has a resistance of 200 newtons. And let's say it's being pulled with a force of 1,800 newtons. We can use this information to work out quantities like the acceleration of the system and the tension in the tow bar. Now, the first thing to consider, so that typically a connected particles question will rely on first taking the system as a whole and then zooming in on one of the objects in order to work out something like the tension. So if they're connected and moving in one direction, the first thing you're going to do is consider the full system. What are the equation of motion here will be F equals ma. So what are the forces acting on the system as a whole? Well, taking this as being the positive direction, because that's the direction in which we're accelerating, taking the full system, we have 1800. In fact, let me move this over here just so that we have a bit more room to work with. We know in the forward direction, we have 1800. And we have the 100 and the 200 acting in the negative direction. So they will be negative 100 minus 200. And these two tensions will cancel each other out when considering the full system. And that will equal to the total mass of 1600 times the acceleration. So as I've done it with the numbers I've chosen, that means that 1500A is equal to 1500 newtons equals 1600A, which means the acceleration is 15 over 16. And then the follow-up question might be something like, okay, now work out the tension in the tow bar. And to do that, you can do it with either of the individual objects. So either we consider the trailer and say so this is the full system. And then for the trailer, we can do F equals ma again. And say that the resultant force is going to be tension minus 100, because the tension acts in the direction of the acceleration, and the 100 acts in the opposite direction, so is negative. So that resultant force is going to be equal to 400 times the acceleration we found before. Now, running that through the calculator, we're going to find 400 times 15, all divided by 16. That's going to give us 375 is going to be that resultant force. And so the tension in the tow bar must be 475. And we can see this is consistent because we can repeat this exercise with the car. So considering the forces acting on the car now, considering F equals ma, in the forward direction, we have 1800. In the reverse direction, we have the tension acting on the car and we have the 200 acting on the car. And this will be equal to 1200 times the acceleration as well. Which means that 1600 minus t will equal 1200 times 15 over 16. Which is 1125, which means, again, the tension is 475. So this is more of a standard warm-up question, one that you would expect to see in the syllabus sort of day-to-day. But let's consider, and I'm going to add one more idea to this mix, which is what is thrust. So if we imagine that now this system is, you're driving the car, you've got the trailer behind you, you're coming up to a red light. Clearly what you're going to do is you're going to stop the forward force, you're going to slam on the brakes in order to slow down. So let's draw that situation. Let's assume that these resistive forces stay the same. Let's redraw the situation, because if the situation changes in mechanics, you've got to redraw it. So now we're going to have the trailer again being towed by the car. But this time what's going to happen is we got these same resistive forces of 100 and 200. We are no longer... Oh, thank you very much, sir. We have someone commenting, where were you when I was in school? You teach really well. Thank you very much. Thanks for the seal of approval. Unfortunately, I was tutoring on an itty-bitty laptop without any access to proper cameras and stuff, but I'm doing my best. So feel free to let me know. You say you're not in school anymore. Are you on a gap year? Sort of resitting? I don't know. Let me know. And also let me know if you have any specific questions. Happy to deviate if you've got something you particularly want me to go through. So now we've slammed on the brakes. Clearly, this forward force not going to be there anymore. What's going to happen is instead you're going to slam on the brakes and create a new sort of force acting backwards. So let's say that's F. We're going to work out what F is. And let's say, so what's going to happen now is there's going to be thrust in the bar. If you imagine it, the car is sort of slammed on the brakes. The trailer doesn't know that yet. So the trailer's still trying to push forward into the car, and it's getting resisted by the tow bar. The tow bar is like being compressed. Instead of being held in tension, it's held in compression. So we're compressing this tow bar. We're pushing in on this tow bar. And what's the tow bar doing? It's pushing back on us. So tension, let's compare that with before. Tension is a force that pulls into the middle, and thrust is a force that pushes out from the middle. Oh, you're working in IT. You did your college, you're now working. Sweet. Well, happy to have you anyway. It's really funny you say that because like my big obsession, one of the reasons I started streaming in the first place is because of a legal streamer named Emily D. Baker, who I reference probably too much on this channel. But I tune in and watch her live trial coverage because I just like the way she explains things. She has such personality and charisma, and she's explaining things that I'm not a law student. I'm not sort of working in the legal profession, but I would listen to that woman explain anything. And so I get what you mean about sort of getting out into the world and sort of still tapping into like professional YouTube, because you can still take away these sort of transferable skills. Yes, you may not be doing exams anymore, but that kind of like presentational skill set, I think is really cool to get to interact with it and kind of, take something on. So glad to have you. I also think it would be really cool if in time, like my audience built out a bit more and there were a few more like teachers and tutors who sort of come through the mix. Because I know I've been approached for a sort of side project and sort of, without going into too much detail, I think it would be cool to sort of get other people in the industry together and kind of, make, because I think legal YouTube is such a thing, medical YouTube is such a thing. I think education YouTube has some building out to do. So very, very welcome. Happy to have you. So the thrust, we're pushing on this tow bar, and this tow bar is pushing back. Thrust is a force that pushes out from the middle. And let's say for the purposes of this question, we got to give it an actual number. Let's say the thrust is 100. Let's keep things in the hundreds, right? We're going to keep the masses the same, obviously. So that's going to be 400 and 1200 kilograms. And what we want to do is to work out this resistive force, or rather, no, I'm gonna change things up a bit. Am I? No, we are going to do this. We are going to do this. Because what we have to do here is to set up similar equations of motion. So the equation of motion is still going to be F equals ma. We need to consider the resultant force and the way it's going to move this system. But again, with any connected particles question, we have a choice about what to zoom in on. We can either take the system as a whole, or we can zoom in on any of the individual objects. Now, taking the system is going to be a problem because we don't know what F is. And that is going to cause the same problem if we zoom in on the car, but we know every piece of information about the trailer. And so for the trailer, we can say F equals ma, where the resultant force is going to be 200 newtons, causing the mass of 400 to accelerate, and the acceleration is then clearly 0.5 meters per second squared backwards. It's decelerating. It's moving forwards, but it's accelerating backwards in order to come to a stop. Now we can apply that to either the car or the system as a whole. I'm going to choose to use the car. So in this case, the forces acting backwards are the ones that will be positive because those are the ones in the direction of the acceleration. So this F I'm trying to calculate, plus 200 minus 100 equals 1200 times that same acceleration of 0.5. So you're going to get F plus 100 equals 600, and then F equals 500 newtons is the force of the brakes on the car slowing it down. We got another comment in. Hi, this isn't relevant, but I just wanted to say thank you. Your interview prep series changed my perspective on them. Thank you very much. That was kind of the point. Oh, congratulations. We got someone who got their Oxford physics offer. Well done. It is a tricky thing to come by, so really well done for getting through that. Oh, all the credit to you, sir. But that's why I started this, right? Is because I think there were things that I really wanted people to get. And so I was demonstrating it initially thinking it would just be for my existing student base. But the fact that it sort of reached even a small, broader audience is actually really cool. So yeah, well done for taking that and running with it, right? Because we haven't met, I haven't seen your skill set, but clearly you were able to take that advice, implement it on your own, and get yourself to an offer. So hats off to you for that. Ah, one of your friends is my team. Wait, okay, I think because it's one of my students passed on some feedback. I think I know the one you're talking about. Greek, without sort of wanting to get into sort of too many personal details. Yeah. He's cool. I like him. No, yeah, he passed on that info actually, and I was like, oh, well done. Yeah, I'm just honestly pleased that it's got to anyone at all. But right, stick around if you want to sort of. I mean, granted, if you're at the point where you're getting Oxford like physics offers, you're probably fine with this stuff right now. But I still want you to understand, because I think this is sort of building up to how to deal with like the lift problems, which is really the main event here. So we've got this idea that horizontally, I think things are a bit more standard, a bit more fine. You've got your tension, which is sort of pulling through, or you've got your tension pulls into the middle and your thrust is pushing out from the middle. And what I had to do with some students who weren't understanding lift problems is to take that exact same idea and shift it into the vertical. So we'll start on the vertical first, not with a lift problem, but with like a sort of a particles in tension problem. So if we have like, for instance, if I move, no, different time, it's fine. So let's say we've got something being lifted up, and let's say we've got these two objects connected where this is being lifted up, and then object A is above object B, and B is dangling from a string. So let's say this has a weight of 50 kilograms, so that will be a weight of 50 G on this particle. Let's say this has a weight of 100 kilograms, so that will be 100 G down. There is some force lifting this up. Let's call it 1500 newtons. And then there will be tension in the string. And remembering that tension pulls into the middle, it means there will be a tension down and a tension down. Now, it's really important, as always, to make sure you isolate your individual bodies and understand the forces that are acting on them. So we can consider, again, the full system, or we can consider any object A in isolation and object B in isolation. And the trickiest part in any one of these is making sure you've identified every single force that's acting on each object. So here, if we're trying to work out this tension, let's first consider the system as a whole, because if we do that, then our F equals ma will turn into 1500 acting up minus 100G minus 50G, and that will equal to the total mass of 150 times, that'll equal the total mass of 150 times that acceleration. So this is actually quite nice, because it's so rare that happens. Mind you, this is not going to be a huge acceleration for the numbers I've chosen at random, but it's nice when they kind of cancel down in a fun way. So because these are all multiples of 150, you get 10 minus G is equal to A, and using 9.8 means that A is equal to 0.2. So we have our acceleration of the full system. Now we can apply that to the individual bodies. I have my choice of A and B. I think the clear choice here is B, because the tension is acting in the direction of the acceleration, which means it will already be positive, and so it will just be easier to isolate. So here, if I say for object B, tension minus 50G is equal to 50 times the A, that will clearly be 10. And so T is going to be equal to 10 plus 50G. And taking G is 9.8, that means I'm going to get a tension of exactly 500 newtons. Which seems off, but there we go. I love when a number just works out like that. Okay, so this, again, seems fairly straightforward. We understand there's going to be tension. But what I had to do, where I kind of had this brainwave of how to explain this, was thinking about the connection here. I said, hang on a minute. If we've got this situation where we have tension turning into thrust, what if we took the exact same idea and applied that to the vertical? Because that's kind of what's happening when these two objects are in contact. If these two objects were instead in direct contact, then B would be pushing up on A, and A would be pushing down on B, and that would be exactly the same as if there was an imaginary thrust bar in between the two. And that was the idea that kind of blew this whole thing wide open for me. So if we consider a lift problem, like a classic lift problem might be something like we have a lift with two boxes on it. Let's say this is 3 kilograms, and let's say this is 7 kilograms, just for fun. It can be quite hard if you do draw it like this, because the objects are all on top of each other. So there's like a tension there. Let's say this whole thing has a mass of, I don't know, 10 kilograms. So well, not 10, sorry, that'll make it seem a bit ambiguous as to what I'm talking about. Let's say the elevator itself had 20 kilograms, and these boxes had 3 and 7. Then obviously we have 7G acting on the box. We have 3G acting on the top box. You can already see it's getting a little bit all on top of each other. And then we have the reaction forces where 3 is pushing down on the 7 and the 7's pushing up on the 3. And it just gets messy. Hate it. Do not enjoy. But I took that idea from that horizontal thrust bar question, applied it to the vertical, and went, okay, let's imagine instead, if I redraw this, first of all, I'm going to draw it as a big rectangular elevator. You imagine there are like imaginary thrust bars in between. So we've got the 3 kilograms. So you can either draw it with the physical bar or without the physical bar. I'll show you both, and you can pick which one is your favorite. We imagine there's a light imaginary thrust bar with no weight. So the thrust bar is going to be pushing out. So instead, if this is being pulled up with a tension, this would be pushing this box up and pushing this box up. So we would have thrust bars, and thrust pushes out from the middle. And now what does that achieve? Well, it means it's actually separated out these reaction forces. It made it much clearer what forces are acting on which object. So if that's A and that's B now, these I will call reaction force 1, and this I will call reaction force 2. And that would be the 7G, and this would be the 20G. In my opinion, it's now a lot clearer which forces are acting on which object, because you can just see them locally. The hardest one for B is to remember about this R1 acting from the top. But what it means is for A, if this thing is accelerating upwards, then we have R1 acting upwards minus 3G equals 3A. For B, we would have the R2 acting upwards and the R1 and the 7G acting downwards, which would be equal to 7A. And for the lift itself, we would have the tension acting upwards. We would have the 20G of the lift, but we'd also have R2 acting downwards. And that would be equal to 20A. And so you can set up these three equations of motion in what I think is a much simpler idea than if you had to sort of isolate the forces from the diagram on the left. The diagram on the right, splitting them out with invisible thrust bars, means that every single force is local to the object it acts on, and it makes it much easier to identify the forces acting on an object and thus set up the equation of motion to help you solve the problem. Plus, it helps you, if they ask for instance, the force of object A acting on object B, sometimes the way to get that is from working out the force of B on A. But from the way I've done it with a thrust bar, those are obviously the same. We're just, in both cases, it doesn't matter whether it's B on A or A on B, they're both R1. And so using this idea of the invisible thrust bar can just like really, really help you simplify a problem and turn it, because like from one of those horizontal ones that people find so easy into a vertical one that people find just as easy. So if I were solving this particular case, I think I would need a bit more information. So I would need the acceleration. Let's say the acceleration was 1. So in this case, it would be fairly straightforward to work out the tension, because I could also still, because they're still connected particles, I can still consider the system as a whole. So I've got my tension acting up. The R1s cancel, the R2s cancel. So that's minus 30G would equal 30 times A, which is 1. And so the tension would be equal to 30 plus 30 times 9.8, which would be equal to 324 newtons. Tension, nice and easy. If we want the force exerted on mass B by mass A, I don't even have to think about what that means. That's R1. How do I find R1? From this equation. Nice and easy. R1 is equal to 3 plus 3G, which should be 32.4, because it's just that 1 divided by 10. And if I want the force exerted on mass B by the lift, I don't even have to think about what that means. That's just R2, which I can use from either the lift equation or from the B equation. My advice is, in general, if you have a choice of equation to work from the equation that uses the fewest number of numbers that you have calculated yourself. Because what you don't want to do is to make an execution error somewhere earlier on in the question and have that bleed through and affect all your further calculations. Now, in this case, we had to calculate both the tension and R1, so it doesn't make a difference. Both equations require us to use one of our own calculated values. So in this case, I'll just use the B equation where R2 is already positive, but that is, in general, how I would decide which equation to use. Showing you as well how that would look if you instead just physically separated them. If you didn't have a full thrust bar in between, you could instead have redrawn it like this. Nope, let's draw that bigger. Also, this is such a thing with Miro whiteboards. Like let's zoom in so it's 100%. We could instead have drawn it as just sort of hanging, just physically separated, where there is R2 acting on both of these, where there's R1 acting on both of these. So there's not necessarily like a physical bar if you don't like introducing something that isn't real, just physically levitating them and separating them so you can see what forces act on which object. Again, can kind of just give you some clarity and make sure you don't miss any of the forces. So let me see how, I think I've got a difficult form of the question like this, which is kind of ugly. And I want to see how that idea might apply to a more challenging question. So let me lay it out. We've got a lift of 250 kilograms. It is supporting a platform of 5 kilograms. And on this platform is a rig which is supporting a mass of 1 kilogram. Okay. So this is a bit more complicated to see how the forces are feeding through, what's affecting what. And again, I'm going to have to simplify it to make it solvable. In this particular case, they give us thrust. So the thrust in this rod, because this thing is being lifted up, the thrust, they give a weird number. I'm going to pick a nice number. I'm going to say the thrust is 100. So remember, thrust pushes out from the middle. So let's say it's 100 of the bar acting on this platform, and it's 100 of the bar acting down on the lift. The question is asking us to find the tension in the string connecting this thing to the frame. So considering all of the forces acting, we know there must be some tension pulling this thing vertically upwards. We know that A is being pulled upwards by the tension in this string, which is connected to the frame. And I think that's all of the forces we need now. Oh, excuse me. So we need to find the tension in the string, this T2, the tension in the string connecting A to the rig. So the way we can do that is to first understand what's happening to the platform. So if we look at this, in fact, what I can do is to simplify this, right? And I recommend that if you ever get a diagram that you think is kind of confusing, let me make sure you can actually see this. Great. So let's draw a simplified diagram. Platform, 100 is acting up on it. 5G is acting down on it. 100 is acting down on the lift. 250 is acting down on the lift. So the one on the left is the diagram as given in the question. You can always redraw the diagram in a way that makes more sense for you. So we've got A. If we get rid of the frame entirely because the frame is light, we can see all of these objects in isolation. We can see very clearly the forces acting on the lift, the T1, the 100, the 250. We can see very clearly the forces acting on the platform, and we can see very clearly the forces acting on A by getting rid of anything that's extraneous that would otherwise sort of confuse or distract us. So now, so we don't know what the acceleration is, but we can work that out very simply by looking at what's happening to the little platform here. So this guy, we can consider F equals ma. The acceleration is upwards, so that will define the positive direction. We have 100 minus 5g will be equal to 5a. And from that, we can work out the acceleration relatively simply. And that is just going to be 100 minus 5 times 9.8, all divided by 5, which leaves us with the acceleration being 10.2 meters per second squared. From there, we can understand how that affects the motion of A. So I'll write down, it may be helpful for you to leave these context clues for yourself as well. This is for the platform. Well, what does that mean for A? Now for A, again, F equals ma. But this time, the resultant force is going to be the tension we're trying to find minus g. And that's going to be equal to the mass of 1 times the acceleration of 10.2. And so tension 2 is going to be equal to 20 newtons. Let me look and see what else they can get you to calculate here. The tension in the lift and the distance the lift ascends in its first 3 seconds. So the tension, let me find the tension in the lift, because that's the one that's most relevant to this skill that I'm trying to go through. Now here, I think the easiest thing to do would be to consider the lift as a whole, because that's the one that T1 is acting on, and I know all the other forces acting on it. And from my diagram, it's kind of clear from looking at the individual objects separated that that's kind of the way to go. I don't think doing the system as a whole is beneficial here. And if I can see that it's going to happen, like I can get there from just considering the lift, that's what I'm going to do. So let's look at the lift. The lift, again, the resultant force is mass times acceleration. You're going to get sick of it. But again, acting up, we've got T1 acting up, the tension we're trying to find, minus 100 minus 250 G is going to be equal to 250 times the 10.2. Just about fit that in. So that means, let me calculate. So 100 plus 250 times the 9.8 is 2,550. And that is 250 times 10.2, which is 2,550. So therefore, the tension here pulling the entire elevator up must be 5,100 newtons. And that's kind of it in terms of how I think you can use ideas that you understand very easily from connected particles horizontally, both considering tension and thrust, but then how those can be applied vertically to understand lift problems. By separating the objects and getting you to consider the forces acting on each object separately. Let me see if I can find any other lift problems that might sort of show this in motion. Yep, I've got one there. Just going to see if I can find any. Yes. Okay, so let's do this other question where, because every one I've considered so far has been accelerating upwards. Let's get one where it's sort of moving downwards instead. So let's say we've got, and I'm going to skip straight ahead to just drawing out the forces acting on the individual objects in the way I think you should lay out a lift problem. Physically separate the objects. So we have box A sitting on top of box B, which I will draw very, very far apart, not touching as they would be in real life. There's a tension pulling the lift up. I'm going to adjust the numbers here. So let's say this was 50 kilograms. Let's say this is 100 kilograms. And let's say this is 850 kilograms. So those are the weights respectively acting on those objects. We also know that because these are in contact, there will be a reaction force between these two, which I will call R1. And there will be a reaction force between B and the ground of the lift. So again, this is sort of imaginary thrust bar situation where there's R2 acting between B and the bottom of the lift. So now let's say in this case, it is descending. So the lift is going down now, and that acceleration I will take as being 2. It's asking us first to work out the tension in the cable, and then the exact language is find the force exerted by box B on box A. Well, that is this R1, but that's just R1. That's the force between A and B in both directions, so it doesn't matter which is acting on which. And then it's asking for the force exerted by box B on the floor of the lift, which again, doesn't really matter because the force between those two is just going to be R2. So it's just asking for T, R1, and R2, by the way I've laid that out. Now, even with my diagram, I probably could have physically separated them a bit more, and I wonder if I can drag and move these. So if I separate these just a bit more, you can see even more clearly the forces acting on each individual object. Ooh, hold on a minute. Okay, I've kind of ruined that. No. No, it's fine. Why have you highlighted the full thing? Doesn't really matter. But you can see very clearly the forces acting on A, very clearly the forces acting on B, and very clearly the forces acting on the elevator, as long as you remember to look up for the tension. So here, let's work these out, again, using these skills. So first, working out the tension. Well, we don't know R1 or R2, so if the first thing they're asking for is the tension, that's indicating they want to take the whole system first. So considering everything on the whole, treating downwards as positive, we're going to do our usual F equals ma. Now the forces, the total forces treating downwards as positive will be 50G acting down. The R1s cancel. We get the 100G acting down. The R2s cancel. We get the 850G acting down. And we have tension acting up. And that will equal the total mass of the system, which I have made 1,000, times the acceleration of 2. So what that means is that 1,000G minus the tension equals 2,000. And so 1,000G minus 2,000 is going to be equal to the tension. And so that tension is 1,000 times 9.8 minus 2,000, and you're going to get 7,800. So that's the tension there. Now, if we want to work out the force exerted by box B on box A, instead of getting tripped up about what means what, Newton's third, and it's just R1. So let's work out R1. How am I going to do that? By considering box A. So from box A, we're going to say that, again, because the acceleration is downwards, that's my positive direction. So 50G minus R1 equals 50 times the acceleration of 2. And so R1 is going to be equal to 50G minus 100 by rearranging. And when I run that through the calculator, 50 times 9.8 minus 100, I get 390 newtons. And then finally calculating R2. I'm going to do that. I'll do it from B. No, I'll do it from the lift. The reason why is because downwards is positive, and I want to keep R2 positive where I can, just to make my rearranging easier. So by considering the lift, I find that R2 acting down plus 850, also acting down, minus the tension I found as 7,800 is equal to the 850 times the acceleration of 2. So simplifying this, what is 850 times 9.8 minus 7,800? It's plus 530 is equal to 850 times 2, which is 1,700. And so the reaction force 2 is 1,700 minus the 530, and that is this many newtons. And that is both the force of the lift acting on B and the force of B acting on the lift. And so that's really what I wanted to go through and just make sure there was a video explaining my method of how to solve lift problems in a way that makes it make sense. It makes it much easier for you to see what forces act on which objects and helps you understand how to find the reaction forces between objects, I think, a lot easier. So I will, as I said, as we're kind of getting into this summer cycle, working on like who wants to show up for the lives, you can see we've got some people in, asked a few questions. I always like to leave time for questions and answers. Not as much today, which is totally fine. So I think I'll end it there early. And the intention sort of moving forward is to kind of create a space where anyone can drop in, ask any questions in a sort of Q&A, making these seminar sessions last about an hour. That kind of happened last week. And so that, yeah. Also, feel free to recommend specific topics you want to see in one of these tutor seminars, because then I can kind of tailor make it for what you most require. I'll come up with ideas as well. Like I've got certain topics that people ask me about again and again and again. I might dip into the physics syllabus. I might dip into the math syllabus. So in the math syllabus, it might be things like circle equations comes up a lot, or nonlinear data in exponentials and logarithms. People ask me for a lot. So having done this a while now, I have a sense of what people like and what people don't like. And so the things that people request from me time and time again, that's how I know to sort of make a video that might be beneficial to sort of a wider audience. So yeah, that's the plan. Then we'll leave it there for today. In the meantime, work hard, have fun. I'll see you guys next time. All right, take care. Bye-bye.